Okay, let's talk master volumes. So the Deluxe Reverb is a fixed bias amplifier. If you look at this schematic here, this is a partial schematic of the output stage. This is one half. This is only one of the two output tubes and one half of the phase splitter. But for our purposes, it explains the spot where we're about to inject bias and also perhaps put in the master volume. So you've got 100K or 82K on the output of the plate of your 12AT7 to a 0.1 microfarad capacitor, a 250K resistor connected to minus 60 volts, which biases the output stage. So if we want to put a post-pi master volume, it's got to be around here somewhere. So, but the thing we got to realize is, well, or think about, is what's it going to sound like when we make these changes? And for that, we need to do some circuit analysis. So what I've done, sliding the paper up here to the next schematic, is I have done an AC analysis of this circuit, and this is what it turns out to be. We have a zero impedance voltage source through the output resistance of this circuit here into the impedance of this capacitor C1, passing through this resistance RB for the bias, and then we measure the output voltage. Now, I haven't put a load of this because it's just a capacitance in the picofarad region, and for our purposes, it's negligible. Now you notice that this RB is connected to ground, and for an AC analysis, that's what you do. A non-varying DC voltages, you just say they're ground. And so this is our AC analysis. And we have some values here. You can calculate the output resistance of that 12AT7, ends up being around 9.8 kilo ohms. RB is, as we noted, 250K. The impedance of capacitor C1 varies with frequency based on this equation. And it is 1 over 2 pi F in hertz, which is the frequency, times the capacitance in farads. Now, once we have all this, we can write a relationship between the input voltage and the output voltage, and it's right here. The output voltage is equal to the input voltage times RB divided by RO plus the impedance of C1 plus RB. It's pretty straightforward. And if we wanted to do some AC analysis of that, we could. Now, if you look at contemporary master volume circuits, this is what some people out there are actually doing. So you have one guy who's replaces the 250K bias resistor with a 250K potentiometer. And one leg of the potentiometer is attached to my 60 volts, and the other attaches to the output of the 0.1 microfarad capacitor, and the wiper goes to the output tube. I don't like this, and here's why. First, this potentiometer, it's a physical device. It gets churned all the time, and eventually potentiometers fail, which means that the connection between the wiper and the legs of the pot will eventually degrade. And that means your minus 60 bias voltage that you're trying to feed to your output tube will change and possibly become interrupted, which is a big problem in a fixed bias amplifier. It's the only thing keeping the output stage stable. The other thing I don't like about it is when you change this value, you change the actual output resistance of this entire circuit, which will change the tone of the circuit as you adjust it. Third thing that I don't like about it is you've got minus 60 volts on one leg of a potentiometer that's on the front panel of your device. The front panel that gets moved from car to car, walks through doorways, could get whacked by anything, could be damaged, and then a musician's hand is going to touch it. I don't like that. Now, some people say, well, you could put a safety resistor between the wiper of the potentiometer and this leg. Yeah, fine. But that doesn't get around the problems of the changing in the tone of the circuit and the fact you've got minus 60 volts sitting on your potentiometer. So another circuit possibility that I've seen recommended is this one, where you move the wiper to the input side of this little circuit, and so the minus 60 volts runs through uninterrupted through the two legs, outer legs of the potentiometer. So this is a little better in that as this potentiometer ages, in theory, the minus 60 volts will not be interrupted. It's also a little better in that your 250K of impedance remains unchanged as well. So that's better as well. However, the tone of this amplifier is still going to change depending on where you got the wiper set, because the impedance will change. And you'd have to account for that in some way. Lastly, you still got your minus 60 volts on that potentiometer, which could potentially hurt somebody. And I don't like that. So I'm going to reject both of these circuits. So this is a circuit that I've actually decided to use. We've got the output stage of the 12AT7 phase splitter to your capacitor C1, in this case it's 0.1 microfarads, into a master volume potentiometer, into another capacitor called C2, and then from there you've got your fixed resistor connected to your bias voltage. This has the advantage that your bias voltage remains uninterrupted from stock, which is something I think is very important. And also, your master volume control doesn't have any large DC voltages on it. Neither, I believe, are good things. So you're saying, okay, that's great and all, but you're adding extra components into this circuit. How is that going to affect the tone? Well, again, we should do some AC analysis. So moving this up like this. This is our AC equivalent circuit. We've got a zero impedance voltage generator through the output impedance of your 12AT7, through the impedance of the capacitor C1, split through two resistors. These model your potentiometer, so depending on where your wiper is set, either RP1 would be larger or smaller, but they both add up to your whatever you choose for your potentiometer value. That goes into your impedance of this next capacitor through the bias resistor and then out. And as I've noted here, your R potentiometer equals to R potentiometer 1 plus R potentiometer 2, depending on where you have that wiper control set. Now this is a more complicated circuit. Now as a result, it has a more complicated transfer function. In fact, this is it. Now, as you can see, it's mighty complicated actually, but it's not too bad as far as circuits are concerned. You've got V out is equal to V in. A little complicated, but we could probably figure it out. So what we have here is I went ahead and put the results of our AC analysis, that equation, into a spreadsheet program and plotted out some values for varying frequency. So this is actually the stock response of that output circuit. So this is 60 hertz here, going all the way over to about 10 kilohertz, plotted on a log scale. And you can see that the response is kind of down, and then it comes up and kind of levels off. And this is just that one particular circuit. If you were to try and analyze the entire amplifier this way, it'd be pretty complicated. But I'm just concerned about this one circuit. So my goal is that if I add a master volume to this, I want to be able to have a look at it and match this response. Because if you don't, then the tone of the amplifier will change. So this is what we're going to attempt to do. So this is what happens if you plug in a 250K potentiometer. You throw in a value of 1 microfarad for the C2 capacitor, which is quite large. This is the result you get. So this top line here, this is the stock circuit, and this is the response of the stock circuit. This red line here is the response of the master volume circuit with the master all the way up. This is response 75%, 50%, etc., on down. Now you can see right here that even when the master is all the way up, the response is not the same. You've got a little bit of voltage loss, but more importantly is the shape is not the same. So when in the lower end, this particular circuit is going to sound thin because you have quite a large reduction in your bass response. And so this is rejected. This will not be used. However, we have some more parameters to play around with to see if we can match the response that we want out of the stock amplifier. So because of that, the first thing I did is I changed the value of the master volume control. So I changed it from 250 kilo ohms to 500 kilo ohms. The response has improved a little bit, but there still is a gap. Now, the problem with using such a large value for your master volume is that it could pick up spurious noise, could make the amp unstable. I prefer to stick with the 250K, but this one gets you a little closer. Now, as you may be aware, there's still some things we haven't played with. For example, the original value of C1 is 0.1 microfarads, and that's the case in this particular simulation as well, still at 0.1 microfarads. What I can do is mess around with that in addition to the capacitance C2, and if I take it off the stock value, maybe I can get closer to the stock response. So I did that. This is with my 500K master volume. What I did is I changed the capacitor C1 from 0.1 microfarads to 0.15 microfarads. The capacitance C2 is 0.47 microfarads. And as you can see, suddenly the response is much closer to what we're looking through for the stock sound. So this is a great improvement. Still don't like the fact that I'm using a 500K master volume potentiometer. So I tried to determine if I could get closer with the 250K, and this is what I came up with. So this is changing the stock value of capacitor C1 from 0.1 microfarad to 0.22 microfarads. C2 is still at 0.47 microfarads. And as you can see, the response is almost exactly the same. We've lost a little bit of voltage, but that may be immaterial. So the plan is that I'm going to start with the 500K master volume, that is this one. And if you run into problems with noise and stability that we can't eradicate with shielded cable or wire dressing, etc., then this is our backup plan right here.